An order in the database, no confirmation email, and nothing in the logs is read. The row's right there. Paid, time stamped, exactly what the customer says they bought. The service that sends the email never heard about it. No exception. No failed job, no dead letter. Just the customer asking where their receipt is. It's 2 lines of code. Save the order, publish the event. They sit next to each other, so they read like one operation. They're 2, no transaction spans both of them, and whatever happens in the gap between those lines, nobody catches. Start with the bug itself. It's a lot smaller than you'd expect. Here it is, all of it. Save to the database, publish to the broker. That annotation on top covers the first call, it can't cover the second one. The broker isn't in your database's transaction and it never will be. 2 systems, 2 commits, nothing that makes them agree. Walk the failure slowly. The insert commits. Then the process takes a sick term, or the pod gets evicted, or the broker call hangs past its timeout. The order is durable. The event was never sent, and nothing retries it, because as far as your service knows, that request finished. So swap them. Publish first, save second. Now the broker's holding an event for an order that rolled back. Something downstream charges a card for a purchase that doesn't exist. You haven't removed the failure. You've picked which version of it you'd rather explain to somebody. Here's what makes it expensive. It never shows up as an error. Error rate's flat. The dead letter queue is empty. You find out because a human tells you. And humans are slow. By then, it's been running for weeks. There's a well-known answer to this one, and it's a good answer. The transactional Outbox. Stop publishing from your service at all. Write the event into a table in the same database in the same transaction as the business data. Then a separate process, the relay, reads that table and does the publishing. One transaction on the right path. That's the whole idea. The code barely moves. That publish call becomes an insert. Both writes land in the same database now, so one commit covers both. If the order rolls back, the event rolls back with it. No window left where one exists without the other. That's the table shape the Bizum's Outbox router expects, and it's become the de facto standard. An ID, what kind of thing changed, which one, what happened, and a body. Look at that first column. That ID writes along to the consumer as a message header. The relay's loop is 3 steps. Read the rows nobody's published. Send them to the broker, mark them done, run it on a timer, or tail the database log. Either way, it's an ordinary background worker, and that's the appeal. No two-phase commit anywhere. I want to be clear here, because the rest of this sounds like an attack, and it isn't. The Outbox works. It closes the hole it was built to close completely with one table and a worker. Every event-driven system I trust has one in it. So here's the question almost nobody asks after they ship it. What did the Outbox actually buy? Run the relay's loop again, one step at a time. It reads a row, it publishes to the broker acknowledges, now it has to mark that row sent, and that's a second write to a second system. The relay dies right there, it comes back, reads the unpublished rows, and that one's still in the list. So it publishes it again. Look at what the relay is doing. Publish, then record that you published. 2 systems, no shared transaction. That's the same dual write your service had wearing different host names. The Outbox didn't remove that problem, it moved it off your request path and into the relay. What you bought is at least once delivery, not exactly once. And duplicates here aren't the unlucky case, they are the design. A relay that can't publish and record atomically has to pick one, risk sending twice or risk sending 0 times. Everything you'll actually deploy picks twice because losing an event is worse. So correctness never got solved. It changed address. Before the Outbox, the thing that had to be right was your write path and your team owned it. After, the thing that has to be right is the consumer. It's the only place left that can tell a real second order from the same order twice. The canonical write-up of the pattern says this out loud. The consumer must be idempotent. Then, in the next breath, it says that's typically not a problem. Both halves are honest. People remember the second half and the requirement turns into a footnote instead of the terms of the trade. To see why no relay can close that gap, look at how they're actually built. A polling publisher is about this much code. Skip locked lets several workers run without fighting over the same rows. Works on any SQL database, which is why most teams start here. It also has a failure mode that surprises people the first time. Rows can come out in the wrong order. A sequence number gets handed out when the insert runs, not when the transaction commits. So a transaction holding a lower number can commit after one holding a higher number. Your poller reads the higher one first. Gunnar Morling, who led Debezium, puts it plainly. Ordering by a sequence column isn't ordering by commit. Locktailing fixes that because the lock gets written in commit order by definition. Debezium reads the Postgres WAL or the MySQL binlog. Events come out in the order transactions really committed. Morling puts Postgres to Kafka propagation in the low tens of milliseconds. Side by side, every row separates them except the last one. Locktailing wins on ordering and latency, and it never touches your table. On duplicates it ties, and it ties at yes. The pattern's own docs list tricky to avoid duplicate publishing as a drawback of locktailing. Your broker's front page says exactly once. Let's be precise about what that covers. Two parties on a network that drops messages can never both become certain the message arrived. Send an acknowledgement and the acknowledgement can be lost. Acknowledge the acknowledgement and you've got the same problem one layer up. This isn't hard engineering, it's proven impossible. Which is the relay's exact situation. It sends the event, the acknowledgement gets dropped on the way back. Now it has two options and both are wrong. Send again and maybe duplicate, stay silent and maybe lose it forever. There's no third branch to write. So what is Kafka's exactly once actually doing? It's real and it's good engineering. You get exactly once processing for a read process write cycle whose input, state and output all live inside Kafka. Confluent's own write-up draws the line for you. Make a remote call or write to a store outside Kafka and those side effects aren't covered. The reason it holds inside that boundary is worth stealing. Kafka keeps the consumer's position in the same place it keeps the data. So committing the offset and committing the output are one write, not two. That's the Outbox move again, one layer down. It isn't free either. On Confluent's published numbers, the transactional producer costs about 3% of throughput. That's measured against at least once with X or against X1, the old default, it's about 20%. Kafka streams committing every 100 milliseconds gives up 15 to 30%. And here's what I didn't expect to find. Debezium supports Kaf Connect's exactly once mode. On the same page that tells you how to switch it on, it says something else. It remains unclear whether the implementation is fully correct or whether edge cases exist where exactly once gets violated. That's the maintainers, about their own feature. None of that is a reason to drop the Outbox, it's a reason to finish it. The consumer half of the pattern has a name too, idempotent consumer. In practice, it's an inbox table. Insert the message ID. Let the primary key reject the second copy. Do the business right in that same transaction. One commit covers the claim and the work, so a replay finds the ID already sitting there. That works when the side effect is a row. Sending an email isn't a row. You can't roll back an SMTP call. So the honest version is this. Claim the ID, commit, then send, and accept that a crash in between loses the email. Or send first and accept sending it twice. You're choosing again somewhere you can see it. Every DDoP scheme has a retention window, and the published ones run shorter than people assume. Amazon's SQS FIFO queues, the one sold as exactly once processing dedupe inside a 5-minute interval. Stripe lets you drop idempotency keys once they're 24 hours old. A window, not forever. 3 shapes, 3 prices. An inbox table takes any message and costs you a row per message plus a cleanup job. If your events carry a value that only goes up, store the highest one you've seen. Compare against that. A watermark, one number instead of a table. And if the operation is naturally idempotent, an upsert keyed on the business ID, you need none of it. So audit the consumer, not the producer. If it only writes rows, you're probably fine already. If it charges a card or sends mail, it needs a key. Size the window against your worst replay, not a round number. And stop waiting on the relay to fix this. It structurally can't. One line to keep if you keep nothing else from this. The Outbox doesn't delete the duplicate. It moves it somewhere one transaction can reach. That's a compliment, by the way. Your service could never put the write and the publish in one transaction. Your consumer can put the dedup key and the business change in one. The pattern buys you a place to stand. Go back to that order with no confirmation email. Add the Outbox and the customer gets their email. Then the relay restarts mid-deploy and they get it a second time. Same row, same relay, working exactly as designed. The ticket only changed shape. Open the consumer, find the operation that can't survive being repeated, and give it a key.